Okay, so I'm going to go over the problems that were posted on the board from the review. So I'm going to start with the first one, which was number 3. All right, so number 3 says, which of the following is a polar molecule? So in order to do this, you really need to draw the Lewis structure out. So for carbon dioxide, your Lewis structure should look like this. And when you guys do your Lewis structures on your test, I highly advise you go through and figure out how many bonds you should be making, unless it's something with an expanded octet. All right, so carbon dioxide will look like this. SF4, let's see, well, sulfur has 6 valence electrons available. Fluorine has 7. 7 times 4 would give me 28, plus the 6 in sulfur. So that would give me 34. All right, so now when I draw it, it will look like this. Fluorine on the outside. I'll distribute the electrons to the fluorines, so 2, 4, 6, and 8. So it's now satisfied, so I can move on. 2, 4, 6, 8, move on. 2, 4, 6, 8, I can move on. 2, 4, 6, 8. All right, so now let's count to see how many electrons we've distributed. It's 2, 4, 6, 8 times 4 would give me 32. So I've got 2 left over. Leftovers will go on the central atom. So this is one of the expanded octets. So in this case, the rule to figure out the number of bonds would not work, but it is a good idea to check it for molecules that are a little bit more simple. All right, so we've got this structure. We've got carbon dioxide. Let's do ZeF2. All right, so now xenon has 8 electrons. Fluorine has 7. So there's 2 of those, so plus 14. That will give me 22. So 22 electrons. All right, so make single bonds, distribute. So 2, 4, 6, 8. 2, 4, 6, 8. All right, so now I have 8 around this fluorine, 8 around this fluorine. I have 16 electrons. So leftover electrons will go on the xenon. So I've used a total of 16. So that's going to be 18, 20, and then I will have another pair right here. So it's actually going to be another expanded octet. So I've got 2, 4, 6 lone electrons, or 3 lone electron pairs around the xenon. All right, so ZeF4 will look like this. All right, and really quick, let's count how many electrons we have available. We have 8 electrons on xenon, and then for fluorine, each fluorine is going to have 7. So 7 times 4 would give me 28. So that should give me 36. All right, so distribute the electrons around the fluorines. And by the way, xenon is notorious for having an expanded octet. So if you see xenon in the compound, it's probably going to have an expanded octet. So 2, 4, 6, 8. All right, so they're all satisfied. So that's 8 electrons around each fluorine. So 8 times 4 would be 32. I still have 4 electrons, so anything left over goes on the central atom. So that's 2, 4, and then that would be all my 36. So I have 2 lone pairs in the xenon. So it's another expanded octet. There just happens to be a lot of expanded octets in this. All right, and then the next one, SO3, should look like this. And there's actually a double bond in there. If you go back and you check, oh, too many electrons there. right, so now we've got the Lewis structure. So that would be 2, 4, 6, 8 for each one. So it's 8, 10, 12, 14, 16, 18, 20, 22, 24 electrons. Sulfur has 6 electrons, so does oxygen, so 6 times 4 would be 24 electrons. So we're going to have a Lewis structure that looks like this. Okay, so we've got all over Lewis structures, so now what we need to do is determine if they're polar or not. All right, so right off the bat, I can look at this one. If I look at the central atom, I've got a linear shape. So automatically, I know that the dipoles will end up canceling. So I've got a dipole going this direction and a dipole going this direction. And remember, dipoles will point towards the more electronegative atoms. These will end up canceling. They're complete opposite directions. So this would be a nonpolar molecule. All right, so now let's look at the next easiest one would be this one. This one, well, if I look at the sulfur atom, I've got 1, 2, 3. I've got a trigonal planar shape. And really, without even looking at the dipoles here, the way that you determine polarity is, first of all, the atoms around the central atom, if they're all the same, that's one way to say that it's symmetrical. And then also there are no lone pairs on the central atom right here. So this one is going to also be nonpolar. So these are simpler when the atoms are the same around the central atom and there are no lone pairs. Automatically you should know it is nonpolar. The last three are more difficult. All right, so what we need to do is we need to look at the shape. So I want you guys to pull out that reference sheet with the shapes on it. Let's pull this out. Oh, not that one. Okay. All right, so now we're going to determine the shape of this molecule and then also determine this molecule and then this one. All right, so this one with the 2 lone pairs, well, okay, if you look it up on the chart, I've got 2 lone pairs and then 1, 2, 3, 4 bonding pairs. So 4 bonding pairs. Here it is. Okay, so 4 bonding pairs and 2 lone pairs. The shape is square planar. So that means that the atoms are going to sit like this in the molecule. I'll have a lone pair going up above the xenon, and then I'll have another lone pair going down below the xenon. And then I'm going to have the atoms coming out at 90-degree angles from each other. So what ends up happening here is that even though I've got lone pairs on the central atom, the way that the atoms end up being situated, all the dipoles end up canceling. So this one is actually a nonpolar molecule. So a square planar shape is nonpolar. So if this one has you confused, you can just know, okay, square planar will end up being a nonpolar molecule. All right, so let's look at this shape right here. Well, we've got 3 lone pairs and 1, 2 bonding pairs. So we've got 3 bonding, 2 lone pairs. It's trigonal planar. So what ends up happening is that the atoms sit like this. So I've got my oh wait, that one's not it. Okay, this one, sorry. This one has 2 bonding pairs and then 3 lone pairs. All right, so the shape is actually going to be a linear shape. And a linear shape means that the atoms are just straight out from each other. So even though we've got dipoles here and we've got these lone pairs, because they actually just end up sitting like this, that means that the dipoles will end up canceling. So really quick, this might be helpful to you. I'll just go through the list and show you which ones are going to be polar shapes. Okay, linear will pretty much always be nonpolar unless the atoms are different. So any linear, and this includes this one, this one, this one, any linear shape is going to typically be a nonpolar unless, of course, the atoms are different. All right, so also trigonal planar will always be nonpolar. The dipoles do end up canceling here. Bent, any bent will always be polar because the dipoles do not end up canceling. Tetrahedral is always nonpolar. Trigonal pyramidal, there's a lone pair on the central atom, a single lone pair, so that ends up being polar. And like I said, bent, any bent will be polar. Trigonal bipyramidal will be nonpolar. Seesaw will be polar because it's got a single lone pair. The dipoles will not end up canceling. Trigonal planar will be nonpolar. Any linear shape is nonpolar. Octahedral is nonpolar. Square pyramidal will actually be polar. So a square pyramidal will be polar because of that one single lone pair on the central atom. Square planar will end up being nonpolar. T-shaped will end up being polar. Linear, any linear will end up being nonpolar as long as the atoms are the same. And same thing here, as long as the atoms are the same, which they're not here. All right, so when you go back and look at these, this was nonpolar, this was nonpolar, this was nonpolar, this was nonpolar. This molecule right here had a single lone pair added to the central atom. So it had sulfur with a single lone pair on it. So this shape is polar. All right, so now let's look at number 4. Number 4 was also on the board. All right, so this is a trickier molecule because of the way that the atoms are arranged and the fact that there's a double bond here. It changes the dipoles. So these are all isomers. And basically what you need to do is you need to look at the dipoles of the most polar bond, which is C and chlorine. So the dipoles will end up going towards the more electronegative atom. So I'll have one going up here and one going down here. Well, overall, because they're not quite going in opposite directions, it may look like it, but they are not. Overall, there is a pole going in this direction. So this one would be polar because the dipoles are not canceling here. If I'm looking at this one, well, I have a dipole going this direction, and then I have a dipole going this direction. These are going to be exactly opposite directions. This would be a nonpolar molecule. All right, and then we have this one. We have the chlorine going this way, chlorine going this way. So overall, I have an overall dipole going down. So this one would also be a polar molecule. So basically, when we're looking at a molecule like this, if the chlorines are on the same side, it's polar. If they're on opposite sides like this, it ends up being nonpolar. All right, I think number 5 was also on the list. Okay, it is. So let's look at number 5. Number 5 says, what is the hybridization of the nitrogen atom and NCl3? All right, so we have nitrogen in the center, and then chlorine around. So you have to look at the Lewis structure again. So let's go ahead and look at how many electrons we have available. Nitrogen has 5. Chlorine has 7 times 3, so that's 21. So I'm going to have 26 electrons here. All right, so single bonds. And distribute the electrons. So 2, 4, 6, 8 around each chlorine. So 8 times 3 is going to be 24. So I have 2 electrons left over. They go on the central atom. All right, so now when we're counting hybridization, or counting for hybridization, remember you're just going to count sigma bonds, and then you're going to count lone pairs. So I have 1 lone pair, and then I have 1, 2, 3 single bonds, and each single bond is going to be a sigma bond. So I have 3 sigma bonds here. Sigma bonds are the only ones that can actually be hybridized. So it's 1 plus 3, so that's going to be 4 pairs of electrons. So that means that I'm going to take 1 s and 3 p orbitals and combine them together to make an sp3 hybridization. So I can just simply count. I will count lone pairs and then I will count sigma bonds. And remember, sigma bonds, you can find a sigma bond and a single bond. So a single bond is equal to 1 sigma. A double bond is equal to 1 sigma and 1 pi bond. And then a triple bond is 1 sigma bond and 2 pi bonds. So you just simply count. I have 1, 2, 3 sigma bonds. I have 1 lone pair. So that's going to be 4 electron pairs. So that means I'm going to take 1 s and 3 p orbitals together and hybridize them to get me sp3 orbitals. All right, I think the next one was 15. All right, so number 15. All right, so place the following gases in order of increasing velocity. Okay, so as long as it's the same temperature, the only thing you're going to be comparing here is going to be mass. So the heavier gases will have a slower velocity. So if it's a heavier gas, it's a slower gas. So if you're going to put them in order of increasing velocity, that means the slowest gas should be first. Remember, these signs mean less than. So the slowest gas will be first, and then the fastest gas will be last. So when I look at this, neon has a mass of 10, O2 is 32, N2O would be 28 plus 16. You have a mass of 44 here, and then for carbon monoxide, that's going to be 12 plus 16, so 28. All right, so the lightest gas will be the fastest, so neon will be the lightest gas, or the fastest gas, and then N2O is the heaviest gas, so it's the slowest gas. So the speed of N2O is less than the next heaviest, which is oxygen, which is less than the next heaviest, which is going to be carbon monoxide, which is less than neon. So it should be choice E. Okay, so heavier gases are slower, lighter gases are faster, as long as they're at the same temperature. All right, so let's see which one was next. All right, 20. Let's look at 20. Okay, so how many sigma bonds and pi bonds are in carbon monoxide? So the first thing you should do is draw out the molecule. I highly advise for molecules like this to check to see how many bonds you're going to make. You're going to get a molecule that looks like this. So carbon monoxide looks like this. So you're going to count sigma and pi bonds. So remember, a single bond is 1 pi bond, or 1 sigma bond. A double bond is 1 sigma bond and 1 pi bond. And then a triple bond is 1 sigma bond and 2 pi bonds. So what we're going to do, we're going to look, we've only got 1 triple bond here. So that means it's 1 sigma and 2 pi bonds. So that's what you're going to get. So it's D, 1 sigma and 2 pi. So when you draw out this molecule, like I said, do the rule to see what or how many bonds you're going to form. So carbon has 4 valence electrons available to it. Oxygen has 6, so that's 10 available electrons. Well, they each want to have 8, so that's 16. 16 minus 10 available electrons would give me 6 electrons that are going to be shared, divided by 2, because each bond is 2 electrons. That would be 3 bonds, and that would show you that you will have a triple bond there. All right, so the next one is 21. Okay, so you have a resonance structure. They gave you that structure, and they're asking for the formal charge on each one. So what you're going to do is you're going to look at each one. So let's look at oxygen first. And you're going to take the number of valence electrons. So we have 6 for oxygen. And you're going to subtract the number of bonds. It has 2 bonds, plus the number of lone electrons. So you have 2 for lone electrons. So you're not counting pairs here like you normally do. You're counting electrons. So 6 minus 6 would be 0. So now let's look at carbon. Carbon has 4 valence electrons. I'm going to subtract the number of bonds. So it's 1, 2, 3, 4, plus the number of lone electrons, which is 0. So 4 minus 4 would just be 0. All right, and then nitrogen. Nitrogen has 5 valence electrons. It has 2 bonds, and it has 4 valence electrons, or lone electrons on it. So 5 minus 6 would give me -1. So the answer should be 0, 0, and then -1. And all of these should end up adding up to the overall charge of the molecule. Okay, so now let's go back and look at some of the other questions. Okay, so let's look at 16 now. All right, so non-ideal behavior for gases is most likely to be observed under conditions of, if you look in your notes, it's right there in your notes. Real gases versus ideal gases. Well, ideal gases, if you calculate something, if you could go through and you do a calculation, your measured pressure should match with your calculated pressure. Your measured volume should match up to your calculated volume. But that doesn't always happen because some gases will have either a larger volume than they should, or maybe even a lower pressure. It just depends. It depends on the conditions. So at low temperatures and high pressures, you're going to see non-ideal gas behavior. And like I said, this is in your notes. But basically, when we have a non-ideal gas, usually what you'll see is that the volume might be larger than it should be. And that might be because the particles are bigger. So normally when we're looking at volume of the gas, we say it's negligible because we're comparing it to the size of the container. And those particles do take a very, very small amount of space compared to that container. But if you have a larger gas, that will not always be true. So your volume might be a little bit larger. And then if you're looking at pressure, your pressure might be a little bit lower if you've got a molecule that has some attraction to the other molecules in the gas. So basically, if you have a polar molecule, those polar molecules actually start interacting with each other, and there's actually some attraction there, which pulls the molecules closer together. And if they're closer together and interacting with each other more, they're not hitting the walls of the container as often, which means that your pressure is actually lower than it should be. Okay, and those are non-ideal gases. All right, so I think, let's see, what one was next? 18. So what intermolecular force or bond is primarily responsible for the solubility of C5H10 into C2H6? Okay, so what you need to do for solubility, like dissolves with like. Okay, so that means polar with polar, nonpolar with nonpolar. Or you can also look at intermolecular forces. So hydrogen bonding will dissolve really well with another molecule that exhibits hydrogen bonding. If you have a molecule that exhibits London dispersion forces, it'll also be soluble with a molecule that has LDF. So like dissolves with like. So what you need to look at is the polarity of these molecules. Well, I have a hydrocarbon that has no nitrogens or oxygens in it, so that means it's nonpolar. This one is the same thing. I don't even need to look at the Lewis structures. If it's a hydrocarbon, it's nonpolar. If it does not have oxygen or nitrogen in it. All right, so you have two nonpolar molecules. Well, if it's nonpolar, its primary intermolecular force is London dispersion forces. Same thing here. So if they dissolve into one another, that's because they have the same intermolecular forces. And in this case, it's going to be London dispersion forces. So if you're looking at the solubility with water, well, water is highly polar and it also has hydrogen bonding. So anything else that has hydrogen bonding will be soluble in that water. So you need to look at the polarity and determine the intermolecular forces. Let me look up. Okay, so the next one is 19 and then 11. So number 19 says arrange in order from lowest to highest boiling point. Okay, so Cl2, you have to look at the polarity and then the intermolecular forces. So Cl2 is nonpolar. Okay, so that means that it has London dispersion forces. And then we have ICl. I don't even need to look at the Lewis structure here. It's just two atoms, and they will have a difference in their electronegativity, which means that they're going to be polar. So there's going to be a difference in electronegativity here. So because there's only two atoms, it will be polar. So you have a molecule that's only two atoms, and there's a difference in electronegativity, it's polar, because there's nothing to cancel out any kind of dipole. So this is polar. It's not hydrogen bonding because there's no H bonded directly to an O, N, or F. So that means it's dipole-dipole. All right, and then we look at Br2. Well, I know it's nonpolar. And I know that means that it has to be LDF. All right, so we're going to put it in order from lowest to highest boiling point. The stronger the intermolecular force is, the higher the boiling point. So I automatically know ICl will have the highest boiling point because it has the strongest intermolecular force. So that's the highest. So now we need to look at Cl2 versus Br2. Well, they're both LDF. So now the difference depends on their mass. So Br2 is the one with the highest mass here versus Cl2. So that means that its boiling point will be higher than chlorine because of the fact that it's heavier. So since it's heavier, it has more electrons and more chances for LDF to occur. Remember, London dispersion forces is when you have a dipole that is a temporary dipole that forms from the movement of electrons. If you have more electrons, you have more chances for LDF. So bromine will have a higher intermolecular force than chlorine. So it should be Cl2, Br2, and then ICl. All right, the last one is 11. So let's look at that. Oh. Okay, 11. Oh, it's a gas law problem. So if the density of N2 gas in a flask is 0.243 grams per liter at 18 degrees Celsius, what is the pressure of nitrogen in that flask if it's heated to 36 degrees Celsius? All right, so we have a temperature that is changing here. We have a density, and we're looking for a pressure. So it actually looks like it's going to end up being ideal gas law combined with combined gas law. So let's pull out the information first. Okay, I know that density is equal to 0.243 grams per liter. So remember, this also means that if I have 2.43 grams of this substance, I have 1 liter of that gas. All right, so I know that temperature, or T1 rather, is 18 degrees Celsius. I'm looking for a pressure here. When it's heated to 36 degrees Celsius. So we're looking for the pressure at this temperature. Okay, so automatically I know that I'm going to have to convert the degrees Celsius into Kelvin. So 18 plus 273 should be 291 Kelvin. You always have to convert to Kelvin for gases no matter what. Okay, so we have 309 for the second temperature. All right, so now I'm looking for a new pressure. Well, unfortunately, I don't know what the original pressure is. So I can't just use combined gas law. So if I want to find the new pressure, I need to find out what the original pressure was. So I could use combined gas law here, but since I don't have the original pressure, I can't just plug it into combined gas law. So I'm going to look at PV equals nRT and see if I can find the pressure that way. Okay, so if I'm looking for pressure, so I'm looking for P1 here. I know that I have R. I also have T, but I need to figure out what N and V would be in order to solve for P. Well, you're going to use your density here. So you know a couple of things. The first thing you know is that you have N2 gas. Okay. So you have N2 gas, so you know what the molar mass is too. You also know that it's going to be 28 grams per mole. All right, so I know what the molar mass is, I know what the density is, and I also know that if I have the density, it's this many grams is equal to 1 liter. If I have the molar mass, it's this many grams is equal to 1 mole. So what I'm going to do here, well, I need to have volume, and I also need to have the number of moles. So I'm going to use my density to do that because it gives me a volume and it also gives me an amount of gas. So if I said that I have 1 liter of gas, I would know that I would have 0.243 grams of that gas. So I'm going to use this information to plug in for V and then also N. So I can use the density in that manner. So if the volume is 1 liter, I know I would have to have this many grams. But I can't plug it in as grams. I'm going to have to convert it to moles. So let's do that first. I'm going to convert my grams of nitrogen into moles. 1 mole on top, and then it's going to be 28 grams. So it's 0.243 divided by 28. I'm going to get 0.0086 moles. So I get 0.0086 moles, and I'm going to also have a volume of 1. So if I have this many moles, I should also have a volume that equals 1. All right, so I have this information over here. I'm going to use PV equals nRT and solve for my pressure, my original pressure. All right, so I'm looking for P. I know that the volume, I'm going to set it as 1 liter. If I have 1 liter of gas, then that means that I have to have this many moles. And I know that R is 0.0821. And I know my temperature is, at this temperature, 291. Okay, so now multiply my moles by R by my temperature. I'm going to get 0.2 roughly. 0.2073, and that's equal to P1. Well, divide both sides by 1. So my pressure here is going to be 0.2073 atmospheres. So I have my atmospheres, or I have my pressure here, but remember this is the original pressure. I want to know what the new pressure is at the new temperature. So the fun doesn't stop. You're going to do yet another problem, or another calculation. Okay, so now I have P1. I'm looking for P2. I also have both of the temperatures. So this is combined gas law. So P1 times V1 times T2 times T1. Okay, so all I'm going to do with this, I'm just going to take out what the variables I don't need. I didn't put N in here, but I'm going to take it out anyway. I'm going to take out everything that I'm not worried about. I'm worried about just pressure and temperature here. So I can take out the volume. So P1 is 0.2073. T2 is going to be 309. All right, and then P2 is unknown, and that's multiplied by T1, which is going to be 291. All right, so I got 64 is equal to P2 times 291. So my P2 is going to be equal to 0.22. So 0.22 would be B here. All right. All right, and that concludes the problems that you guys put on the board. So.